Hello and welcome to the second part of our presentation. It concerns the project Coherent Optical Wireless System for Next Generation Home and Corporate Networks, or in short, CAOS. My name is Thomas Kamalakis. I am from the Harokopio University of Athens, the Department of Informatics and Telematics. Now, in the first part of our presentation, we discussed some general features of optical wireless technology. Coherent detection can pose significant pros in implementing optical wireless systems. And now we are going to look in the second part of our presentation. We are going to discuss first of all some application scenarios. That is, where this ultra-wideband optical wireless coherent based technology can be used. Of course, the first application that comes to mind is the scenario from home networking. We can understand that in the advent of fiber to the home, data rates coming to the home gateway, that means data rates that are available for the user access, will be significant. Will be much more significant than the 24 megabit per second offered by ADSL. So we understand that as the access rates increase, we may need more broadband technology in order to distribute these high data rates inside the home network. This is currently done with Wi-Fi, and quite easily so, because Wi-Fi can reach about typically 54 megabit per second. Some versions already commercially available can distribute up to 100 megabit per second data rates. Of course, this is an aggregate data rate, and this is a nominal data rate. Data transfer using Wi-Fi, you can try it with your own laptops inside your home network, is actually somewhat lower than these nominal values. And these data rates are all shared. I mean, you don't get 100 megabit per second for connections, for point-to-point connections, but this is an aggregate data rate concerning, let's say, the entire network. All the terminals, all the TV screens, the laptops and stuff like that share this data rate. So we can understand that as soon as data rates that are reaching our apartment, our house, or what have you, increase beyond 100 megabit per second, which is the case with fiber to the home, there is certainly a problem how you can distribute data. We should also point out that traditionally the in-home networking technologies were supposed to offer about a tenfold increase in data rate compared to what actually arrives at the home gateway. That is because you don't have only outgoing and incoming traffic, you have inter-home network traffic. That is, you may have an application server, or you may have a media server somewhere in your house, and you want to distribute data to your laptop to stream movies and stuff like that. Usually, the streaming requires much, especially for high definition and 4K quality, it requires much higher data rate than that is available at the gateway, because of course this is okay because the data sharing is done um, inside the network. You don't stream from somewhere else outside your house. You stream from inside your house, but this poses significant challenges for Wi-Fi. And of course, you could consider some kind of wireline networking technology that is abandon the wireless scenario altogether, but this poses some important limitations in user mobility and other installation-related difficulties. Uh, the most important thing is that you are bound with the wall socket, whether this is UTP cable or some form of fiber cable. You are bound by the sockets you have on the wall. Sockets, I mean data sockets. Network data transmitting sockets, like the UTP sockets that we have in our office network. And uh, you will soon witness, if you want to connect many devices that are not near these wall sockets, you will witness the effect commonly referred to as the cable spaghetti. Cable spaghetti is a very disturbing effect. You would prefer not to have too many cables running out of the wall sockets with multiple hubs, let's say, that you use to connect many terminals to one socket. Those of you who use desktop computers are already accustomed to some form of cable spaghetti. Imagine having a secondary cable spaghetti effect due to the networking and not just the desktop connections with the keyboard or stuff like that. In any case, in most homes, in most houses, we tend to try to eliminate this cable spaghetti, mainly because of decorative reasons. Now, the two scenarios that are considered, and in which the coherent optical wireless system can be applied, are shown in this slide. In one case, these are very similar scenarios. The main difference is what arrives at the building gateway. This is a fiber to the building scenario where, this is the right one is actually a fiber to the building scenario where a 10G EPON line reaches at at the building gateway, which is placed at the basement, let's say, of the building, and using the apartment's fibers, this gateway distributes the data to the various users. This is certainly a practical scenario. Of course, you need a router, a rather large router at the building gateway, depending on the number of flats and users that are connected to this to the switch. And what you do is that you have, let's say, one or a fiber pair for each flat, and using this fiber, you deliver the data to the ceiling, let's say, of the room, where you have an optical hotspot, a coherent optical wireless hotspot, and this sends back, transmits and receives data from your terminal devices. Either these are high definition televisions, some user desktops or laptops, and media server. we will see that 2 gigabit per second communication and even 10 gigabit per second communication can be achieved with these with the COWS technology for a relatively low power. So this is certainly a viable solution for delivering high data rates to your terminal devices. Now, the alternative scenario shown in the left is actually somewhat fiber to the home scenario, where you actually use wavelength division multiplexing. That is, each apartment has its own wavelength for transmitting and its own wavelength for receiving data, and the basement, and there is a passive wavelength splitter at the basement of the building. All wavelengths arrive simultaneously with the carrier fiber, and the wavelength demux demultiplexes the available wavelengths and distributes each wavelength to each flat. Distributes the corresponding wavelengths to each flat, and from then on the solution is the same. You use the apartment fiber running through, let's say, the ceiling, and to connect to the COWS hotspots, and the COWS hotspots are able to deliver multi-gigabit wireless connection to your terminal devices. Now, of course, you can envisage the COWS technology applied to office networks. The scenario is somewhat different, depending, of course, of the size of the office. In a small company, you usually in a small, let's say, company like the ones you have in Greece, you usually have small businesses in apartment offices, in one-story offices, where you have a server room containing all the servers that are required for various services offered to the people employed in the company: email server, application servers, roaming profiles, or whatever this is. These again, you have the carrier's fiber reaching in a gateway switch, and you use again a fiber network to distribute the data inside the office network. The idea here is the same. The connections with the servers can be done wirelessly, because, as we will see, the COWS link can support, as I said before, multi-gigabit per second connectivity, and the various terminals can again, or the workstations can be connected wirelessly with the COWS hotspot. In fact, one hotspot can be associated with one or two terminals, depending on the coverage specifications that we will see next. Okay, so this is quite similar to the home scenario. The network architecture is a bit different, in the sense that you usually need to connect many more servers. And now this is an interesting thing here, because this also suggests that in the server room you will be able to connect the servers wirelessly, and this brings us to the third application scenario, which is in applying the COWS technology to large data center networks. This is of course a very interesting approach. There are several, if you look at the literature in the the worldwide literature, you could see that there are some groups currently working on wireless data centers, but these are implemented using 60 gigahertz technology. 60 gigahertz has its own problems, and the bandwidth is not as vast as in optical wireless. So you would think that some level of wireless interconnection in data centers can be done through the cow's links, and you may wonder what is the actual benefit of using wireless connection. First of all, if you go to large data centers, you see many fiber or other types of cable, and besides this spaghetti effect that we discussed for the whole networks, because of this large amount of cabling, of this vast cabling, results in heat, because the fibers tend to occupy a large amount of the available space, so you get some heat related you have to manage this extra heat that you wouldn't have if you did not need fiber cables that limit the space available for heat dissipation. And of course, you have some kind of inter server communications. These are all servers in the bottom layer that are on the same rack. This could also be done with a cow's hotspot, or this could also be furthermore be an IMDD, a simple IMDD optical wireless link. It depends on the available power and on the data rate specifications. And as you proceed you start to interconnect the data, the racks between themselves. You could also use such coherent optical wireless links. Of course, in the edge or aggregation level, the data rates are much higher, but they could be served with properly designed coherent optical wireless link. That is, you don't only have some gain in the connections of the server which are placed in the same rack. You have some gain because you can wirelessly connect servers located in different racks. And another point to consider is that you can also connect racks or data center networks which are not in the same building, but are in a nearby building, and you can achieve this connection with an outdoor coherent optical wireless link. This of course allows much flexibility. When you want to change a server, you don't have to, of course, to unplug the cables, reconnect them. It should offer a much more flexible network design. Now, what is the proposed system architectures that we discuss in the project. Mainly, we are concerned with the transmitter and the receiver. Of course, the terminal can have usually has a transceiver, that is a device that transmits or connects. Transmits and receives the data. So on one transceiver side, you start with the laser. This should be a narrow line with laser. We shall discuss the line with requirements. The line with requirements in some more detail. Now, this laser the laser beam is divided into two parts. This can be done with a standard 3dB coupler. The upper part, let's say half of the laser power, feeds a modulator, an IQ modulator. This is a device that is used to convert voltage signals into light signals. The IQ modulator is a special kind of modulator. It can allow you to imprint both amplitude and phase changes in the laser beam. Remember that the laser beam is coherent, so you could in principle change both its amplitude and its phase. And the modulator transmits the data to open space, but before that you need some kind of transmitter optics. These are now, as I was saying, the architecture of the system comprises of the transmitter side. The modulator transmits the data to open space, but before it does that, there is a need to beam shape, to do some beam shaping. This is done with some lenses, special design lenses at the what we call the transmitter optics. This is a series of one lens, two lens system, depending on what is required. On the receiving side, now there is the one half of the laser power goes to the coherent receiver. This is this unmodulated laser light acts as the local oscillator, and the incoming beam from the other side reaches the receiver optics. The receiver optics are used to focus the beam inside the coherent receiver. Now, at the other side, there is another transceiver. Let's say this is located at the ceiling. The left transceiver is located at the ceiling. The right transceiver is at the receiver terminal. It is more or less the same. It has one transmitting side and one receiving side. Now, what kind of system components do we use? These are standard components used in coherent detection systems. The transmitter side, this is a modulator. The modulator consists of a Mach-Zehnder interferometer that uses some phase modulators to generate the I and Q components, to imprint the I and Q components more correctly to the laser beam. The separation with the I and Q components is done with this phase half pi phase modulator. This adds a half pi phase difference between the two arms and ensures that these two components are separated by 90 degrees phase difference. Now, at the receiving side, the key component for the coherent detection to work is this hybrid system. It consists of 4 3D couplers, and again we use a phase modulator to imprint a 1/2 pi phase difference. This is what generates the this component is used along with some photodetectors to generate the I and Q components at the receiving side. These are standard components. They can be found either on integrated form, but they can also be used. One can also use discrete components to implement them, but of course this increases the overall size. So this is the second part of our presentation. I would like to thank you for watching this.